Welcome to the next lecture of mechanics of material. So in this lecture we are going to discuss about torsion. So what is torsion is nothing but twisting or wrenching force on an object. For example, if someone is trying to twist your elbow, then the type of force is called as a twisting force or a torsion. Okay. So in today's lecture we are going to discuss about the derivation which is we are going to do for torsion equation. Before understanding that, let us take some few of the assumptions before taking the derivation of torsion. So first of all, we have to make some assumptions for torsion equation or torsion formula, right? Okay. So we will go for the derivation. Before getting into derivation, we should have some assumptions regarding the shaft. Generally, if we are doing shear force and bending moment diagram, we will go for few assumptions like beam is under equilibrium. So those things we go. So similarly, in this first thing we make is material which we are considering should be an uniform material. The material which has been made for the shaft should be an uniform material. It should not be an ununiform or what we say somewhere the material is some other parts the material is less. It should not happen. So next is the circular shaft remains circular even after application of applying load, you can write after applying load. Okay. Next is the plane section on shaft, means if you are considering a shaft like this, I am cutting here. So this plane which is normal to the shaft on the shaft, normal to the axis, should remain normal after application of load. Okay. Next is twist along the length is uniform. Twist along the length is uniform. So wherever you cut the material, you will get same angle of twist. Twist along the length is uniform, we consider. The next is distance between the two axes, distance between two normal planes remains same after twisting. Even after twisting also, the distance between the two normals should be remain same. Okay. So the next point is the maximum stress induced in the shaft, maximum shear stress induced in shaft remains within elastic limit. So the whole thing should be, these are the few assumptions before getting into the derivations. So let us see the diagram first. So before getting into equation, that I will write here torsion derivation. Okay. So before getting into derivation, let us see. So first of all, let us draw the diagram. I will draw this. So this is my circular shaft. Okay. Clear? So this circular shaft, when you try to apply a moment, the moment, in either clockwise, anti-clockwise. I am considering here clockwise direction. So, because of that what happens, this side will get twisted. Okay. So, when it gets twisted, let us this take the position M. So, it has been distorted to the second position D naught. So, because of that we will get some strain. What is strain? Is nothing but change in length by original length. Similarly, this part I will draw here, so that you can have the clear picture of it. So, this is the torsion. So, this is a circle. So, if this has been distorted, when you join both the sides to that center, here you are going to get an angle theta. So, this is your M original, this is your M, clear. So, in this way the material is getting deformed, or the what we get, stress is being obtained in this like this. So, this is the diameter of the rod. So, the length of the shaft is considered as L. Okay. Now, the first thing we have to write in this derivation is, consider a moment M is applied to the shaft which is fixed at one end and free at other end, same as cantilever. So, it is fixed at one, another is fixed other. Okay. Now, the shaft has distorted from M to M dash, you can take it C to C dash, you can take it A to A dash, no problem. Okay. Now, because of this distortion, obviously we are getting shear deformation, that is, we write shear strain we are getting on the whole surface, it is getting distorted. If you take your hand, you twist your hand like this, if you twist your hand, you can see that whole area is getting distorted. So, shear strain is equal to, we generally write shear stress by modulus of rigidity. Now, shear stress is tau, modulus of rigidity C. So, this is as per general formula. Now, if you see from the diagram, so see this diagram. So, from the diagram we can observe that it has been distorted from original position this to this, or okay. So, this has been distorted, which we have taken M dash. So, here your phi is coming, which you generally consider shear strain as phi. If that is nothing but tan phi we generally take, but if the phi is very small, we can consider tan phi as phi. So, clear. So, shear strain is equal to, you can write as here this phi. So, now this phi is equal to M dash by L, that is nothing but whatever is the change here obtaining by the original length L, clear. So, this is the figure, I will separate it now. Okay. Now, so this is also shear strain, this is also shear strain, both should be equal. So, I will do tau by C is equal to M dash by L. So, till here clear. Now, take that circle in which we got M dash with respect to the angle with respect which is obtained at the center. This is your center part, this is your M dash, this is your theta. We know that what is the length of this whole surface, length of this whole surface is 2 pi r, where 2 pi is nothing but 360, r is the radius of the circle. Now, this M dash is nothing but this r into per what angle we have made, that distance we have to take. So, the distance M dash is equal to M dash is equal to r theta, correct. So, this is for total 360 angle, this is for particular angle theta, clear. So, I will write tau by c is equal to r theta by L. Okay. So, this will rearrange as tau by r is equal to c theta by L. This is the first half of your derivation. Let us consider this as 1. Let us consider this as 1. So, one half has been completed. Let us enter into the second half. So, here with respect to this relationship which we have got, tau is equal to tau by r is equal to c theta by L, along with that we are going to obtain some torque. Okay. Obviously, when you are trying to twist your material, you will get some torque. So, what is torque is nothing but force into distance. Okay, correct. This is the same as moment, force into generally distance. Now, for example, this if you are opening a door, you will get some moment, you will get some torque to rotate it. Okay. So, the same thing happens here also. Now, the torque is equal to force into distance, but what is this force? So, this force is nothing but shear force, we generally write torque is equal to shear force into the distance. So, what is the shear force? Shear force is equal to shear stress into area. So, which area we have to take? For simplicity, what we will do is, so this is your circular part on which your shear stress is coming, the shaft, the cross sectional part of your cylinder shaft. Okay, I am considering a small element on which your shear stress will be acting. Okay. So, this is from center, let it be at a distance of x, and thickness of it be dx, thickness is dx. Now, you can write here, consider a thin elemental circular ring of thickness dx at distance x from origin. Clear? Now, this element will experience a shear stress of tau x. Now, shear force on element is equal to tau x into area of circular element, correct. So, tau x we know, we will consider as it is, but whereas area how we will take. So, this is a circular element. What I will do is I will cut it into a part here, I will bisect it. So, if I extend it, it will become like this, correct. So, the thickness is here, it is dx. So, the length, it will become the circumference of the circle, which is 2 pi x, circumference will become 2 pi x, that is equal to tau x into area is nothing but 2 pi x into dx, because the shear stress will act parallel to the surface, it will act on the parallel to the surface, it will not act along the axis, it will act exactly parallel to the surface. So, this is the shear force acting. Now, with respect to this shear force, we have to calculate the torque. So, now, torque is equal to this force tau x into 2 pi x into dx into distance. So, this generally we take the distance with respect to origin, because if you try to rotate here, it will rotate in another way, like if I am rotating from this point, it will rotate other way. If you rotate like if I open this, if I rotate from this angle, it will try to rotate in different way. So, with respect to the radius, it is changing. So, we are now trying to rotate the torque is acting on the element which is at a distance dx. So, this is your x. So, this will become tau x into 2 pi x square dx. So, this is your dt you can take, because this is acting on a small element. Now, total torque T is equal to 0 to r of dt. since the element is a small element and this is being changed from 0 to r, this is a maximum circular distance, so into T r. So we will write 0 to r tau x into 2 pi x square into dx, correct. But whereas here whatever the tau you are having, that is for the particular element, but when it is for particular element you have to make it for the whole surface. How to make it for the whole surface? That is nothing but, for example, if tau x is acting on a length of L, then tau r will be acting on r, which we will consider as tau is equal to tau r is equal to for a length. Now if I want to replace this tau x, now I want to replace this, simply what you have to do is you have to take the ratio of this, tau x by tau is equal to x by r, then tau x is equal to tau into x by r. So tau x is equal to tau x by tau is equal to x by r, tau x is equal to, okay. So with this we will get the value of t, that is t is equal to integral of 0 to r tau by r into x into 2 pi x square into dx. So this x again multiply, so it will become 0 to r tau by r of 2 pi x cube dx. So in this tau is for the whole surface, so we have considered, so this tau by r and 2 pi are common, so we will write tau by r 2 pi integral of 0 to r x cube dx. So this will become tau by r 2 pi x raised to 4 to 4 in between the limits 0 to r. So that is tau by r 2 pi into r raised to 4 by 4 minus 0, okay, clear. Now 2 1s are 2, 2 2s are 4, this will become tau by r pi r power 4 by 2. So here we have a small topic or small thing, as we have discussed about the moment of inertia, m is equal to pi by 64 d power 4. If this d is converted to r, it will become 2r, so then it will be pi, so 2 to the 4, 4 to the 8 to 16, 16 r power 4 by 64, this will become pi r power 4 by 64, pi by 4. So this is for moment of inertia. Similarly, this value can also be turned into this type, that we generally call it as polar moment of inertia. For that I will convert this radius into diameter d by 2 the whole power 4 whole divided by 2. So this will become tau by r, okay, shear stress tau by r into pi into d to the power of 4 divided by 32 will get. Why means, so this is 2 to the 4, 4 to the 8 to 16, 16 into 2 32. So this is the value. So this pi d power 4 by 32, this is pi d power 4 by 64, this is moment of inertia, this is polar moment of inertia. We will write this as polar moment of inertia. Now, so t is equal to tau by r of ip we have got. So I will write it as t by tau p is equal to tau by r. So this is your equation 2. I will show you the equation 1. So see this equation 1 and 2, compare this. Okay. See this, tau by r is equal to c theta by l, t by ip is equal to tau by r. So tau by r, so this will become t by ip is equal to tau by r is equal to c theta by l. So this equation is called as torsion formula or torsion equation. This is same as m by I is equal to sigma by y is equal to E by r. So this is momentum equation, moment equation, but whereas this is torsion. These two formulas are your base for your third and fourth unit. Torsion is your fourth unit, moment is your third unit. So in this way you have to remember m by I is equal to sigma by y is equal to E by R. Similarly, tau by IP is equal to T is torsion, I is polar moment of inertia, tau by R is equal to C theta by L. Here in polar moment of inertia we have only for two values. I will write here. So what are the equation? I will rewrite the equation and I will rewrite the terminologies. So T by IP is equal to tau by R is equal to C theta by L, where T is torsion, not torsion, this is generally we call it as torque. Okay. IP is polar moment of inertia. Polar moment of inertia, polar modulus of inertia, whatever you can write. Tau is your shear stress, R is your radius, C is your modulus of rigidity, theta is your angle of twist about which the material, the shaft has been twisted, L is length of shaft. In this polar modulus of inertia, would have only for circular elements, that is polar modulus of inertia for solid circular shaft. Remember these two values, that is more than enough for you. Pi by 32 of d power 4. Hollow circular shaft, the value will be pi by 32 of d power 4 minus small d power, where capital D is outer dia, smaller d is inner dia. Okay. So outer dia, inner dia. So these two values you have to remember. Other than this, we have three small formulas which will be repeatedly asked in your questions. So one is torsional rigidity. First thing is, so we will see those important formulas itself. Torsional rigidity. So what is this torsional rigidity? Is nothing but, for example, from the curve T by IP is equal to, we have C theta by L, correct? So the twist which you have obtained for the torque per unit theta, for a 1 degree of twist, how much amount of torque is required, that is called as torsional rigidity. This is generally indicated as K. So this value depends upon modulus of rigidity, polar moment of inertia or polar modulus of inertia, and length of the shaft. If length is more, a small twist, small force will be tried to rotate it by larger angle. If length is small, you require more amount of torque to rotate it by 1 degree. Okay, so the torque is inversely proportional to length, that also we can able to see. The next thing is power transmitted. So generally why we are studying about this torque and all this thing is nothing but, so we generally transmit the powers by using this type of torsional activities. So for example, if you see your what do we say, shaft, for example, if you see your shaft, whatever shaft you take, axle, gearbox, so all are mounted on a particular shaft which generally rotates. So while rotation it will be have some torque, and by rotating itself it will transmit your power from one shaft to the other shaft. So the power transmitted by this is nothing but, we know that generally power is equal to force into displacement. So, what is the force here we are discussing is shear force itself, force into the displacement which we are obtaining is in terms of circular. So, that we generally write it as 2 pi r circumference of circle into number of turns which are obtained with the circumference of circle divided by 60. So, from here this f into r we can make a group, and 2 pi n divided by 60, this f into r is nothing but called as T. So, this is most generalized formula where T is your torque and N is your number of revolutions. RPM, we generally write it in RPM. Since it is in RPM, to convert it to seconds itself we have divided with 60. Okay. Next is modulus of rupture. Next is modulus of rupture. So, what is this modulus of rupture is nothing but it is defined as maximum fictitious shear stress, maximum fictitious shear stress required for maximum torque is called modulus of rupture. So, generally they will ask definitions in this. So, shear stress rupture is equal to tau max. So, tau by IP is equal to T by IP is equal to tau r in tau by r. So, that r on r, what will be the maximum torque depends upon the rupture shear stress. So, these are the few formulas which will be repeatedly asked. Thank you. We will discuss the problems in next lecture.